Hello, Precalculus. I hope the quiz went well. I'm sure you all did fantastic. We should be talking about it next time we meet. And we're also going to be working on 2 more sections next class. So that's what we're going to do with this video today, is take some notes on sections 3.1 and 3.4. 3.1 is about linear functions. 3.4 is about quadratic modeling. So a lot of this stuff should be familiar, but maybe asked in ways you're not used to. So there's the date. These are the sections. Reminders, just in case you haven't seen them in a little while. Your midpoint formula, your distance formula, check those out before we begin. So section 3.1, our linear functions and models. Our linear functions, f of x equals mx plus b, for like what, the millionth time. M is our slope, b is our y-intercept. Something we haven't talked about this year, I'm hoping that you remember. What about the domain and range? Domain and range of linear functions, well, the domain, you think about it stretching left and right along the x-axis. That's all real numbers. Hopefully you've seen that before. That is all real numbers. The range is also going to be all real numbers because it's going to go, it's got a slant, or, well, I guess, what range? It might be one number if it's a certain kind of function, but in general it's all real numbers as long as m is not 0. The slope is undefined. Don't worry about it. There are 3 ways that we can kind of quantify our slope. Slope can either be increasing, decreasing, or constant. So let's do 2 quick examples of that. What if I were to draw this and I just gave you a line like that? So there's example 1. And how about example 2 over here? What if I were, let me use a different color. If I were to draw something like that? I'm sure you already know the answer, but for the sake of being thorough, this line is from left to right going upwards. We call that increasing. From left to right, this line, even though I can't draw that way, is remaining flat. That slope is constant. That function is constant. Decreasing will be decreasing from left to right. Let's take a look at intervals of increasing and decreasing. So let's draw a quick sketch. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The most exciting part of the video is now over. So let's draw something that does something like this. Make sure to make noises while you draw your curves, otherwise it's no fun. You can't even see what I am doing. I am sorry about that. I'm not going back and fixing it. Let's talk about intervals where this function is increasing and decreasing. So our increasing intervals and our decreasing intervals. This definitely comes into play a lot when you think about calculus. We always go from left to right, like reading in English. We see that this is increasing to there, and you see my awful drawing. That isn't exactly right, but let's go with it. It looks like from negative infinity all the way up to negative 3. Looks like it's increasing. From negative 3 all the way down to here. Looks like from negative 3 to 0, it is decreasing. Finally starting at 0 again. What do we notice? The graph is now increasing as it goes to infinity in the x direction. I'm hoping you remember interval notation. Let's start with our increasing intervals. Infinities always get parentheses, goes up to -3. We're actually only going to do parentheses for this because you can't be increasing or decreasing at a point. And then we're going to union that with our other interval, 0 to infinity. Where's our decreasing interval? From -3 to 0. That is not the point, -3, 0. That is the interval, -3 to 0. Let's talk about average rate of change, another big calculus topic. I guess maybe not as big. Seems big at the start. Average rate of change. Might abbreviate it as AROC, average rate of change. Thinking about it from the point AF of A to BF of B to random points. This might look familiar if you think about it hard enough. What is the average rate of change? F of B minus F of A over B minus A. Now you might say to yourself, that feels familiar. That's because if the function is linear, average rate of change is simply the slope. For lines, average rate of change is the slope. So two quick examples. I'm at the end of my paper. F of x equals -2/3 x plus 5. And how about f of x equals 4? When we are asked for the average rates of change, when they're linear, we're just being asked for the slopes. So what's the slope of the first one? -2/3. What's the slope of the next one? 4. Just kidding. It's not 4. Please don't put 4. How much is it changing? How much is it increasing as it runs? 0, the slope. 0. Totally got you. No, I did. All right. Next thing I'm going to do is I'm going to pause. I'm going to make some tables. We're going to talk about how to get, or how to tell from a table whether something is linear or not. And just like magic, there are now tables. Look at us go. You might have to pause and write them down. How do we figure out if a table of values gives us a linear pattern? You just got to look for constant rates of change. Looking over at the x values of this first table, hopefully you notice they always increase by 1. Looking over at the outputs, they're always increasing by 3. These changes remain constant. These changes remain constant, so this one is linear. In fact, we can come up with the equation of the line that gives these values. Remember, our slope is change in y over change in x. Well, the change in y is 3 every time. It's 1 for the x in this table. So the slope is 3. Do we have our y-intercept? Certainly. So our now y equals f of x equals 3x plus 11. Fantastic. Looking over at the second table, you'll notice when we look at the x's, we're going up by 1s again. So the change in x is constant. Looking at the y's, this goes up by 0.03. This goes up by 0.04. This goes up by 0.06. This goes up by 0.07. That one isn't linear. And I don't know if we need to figure out what kind of function it is. I mean, if we have no idea, it's not really helpful just to assign a function to it. I mean, in the real world, you can model things, best approximations, but we're just figuring out if it's linear or not. Okay, now we got a big problem here before we move on to quadratics. So again, I'm going to write it down. So I'm going to pause. I'll be back in a hot second, and we'll get to our big problem. All right, it's an application of some linear ideas. We can think about some basic supply and demand questions. So this is something you're going to be doing in class. Let's say that the supply, given a price P, can be represented by this orange function right here, S of P equals 60P minus 900. The demand can be represented d of p equals negative 15p plus 2,850. And the questions you're going to be answering amounts to find the equilibrium price and then the equilibrium amount too. So we're going to get that done. What is the equilibrium price? That is the price where the supply and the demand are the same. So in like the real world context, that is the price you'd want to sell at because you're making just the right amount and you're selling all of it. You don't have any extras, so you're not using extra money to produce more, or you're not running out of stock and people are getting mad at you if the demand is too high. One way to think about this is graphing. We're certainly not going to graph this every time, because especially without graph paper, man oh man, this is going to look bad. 60. Holy cow, yowza. What is that? It goes through 15. These lines are going to look bad, guys. So there's my supply line. How about my demand line? 2,850, 2,750. So it's probably going to be like there-ish. Negative 15. Oh, where's that going to hit the x-axis? What do we think? Please solve for it, right? I guess I probably should have done this beforehand. That would have been a good teacher. But what are you going to do? 190. Did I draw enough? 10, 20, 30, 40, 50, 60, 70, 80, 90. So let's draw that line over there. And I'm probably going to miss. This is an awkward angle. Yeah. Not too bad. All right. So where the supply and the demand are equal, that is the equilibrium point. And what's our equilibrium price? If I drew this perfectly, it's going to be down there. Looks like it's supposed to be about 50. We'll see if that works, but again, this is just a sketch of the graph, so it could be off a little bit. How are we going to find the equilibrium price? That's when the supply equals the demand. So we're going to do S of P. When is that equal to D of P? So really quickly, I'm going to run through this. I'm hoping you're okay with me kind of just flicking my wrist and thinking about this as I go. Your price, equilibrium price, will be $50. My graph turned out pretty good. Not perfect, pretty good. Go me. What is the equilibrium amount? Plug in the equilibrium price. In either function. They're equal at that point. So the output will be the same at both. So let's do just S of 50 equals 60 times 50 minus 900. 60 times 50 is at 3,000 minus 900. So our equilibrium amount is 2,100 units of whatever this item is. All right. We have 3 quadratic modeling questions coming up. I'm just going to pause. I'm going to reset. You maybe stand up, take a break, stretch out a little bit. I'm hoping to get these next 3 problems done in like 10 minutes, and yeah, I'll be back in a sec. Hello. So this is kind of unfair of me. Here's a word problem that wasn't there a second ago, so you might have to pause and write some things down if you need to write anything down, but I'm going to read it. A farmer has 600 meters of fencing to enclose a rectangular field along a river. No fence is required along the riverside. What is the domain? Find the maximum area. What are the dimensions of the field? So we have this river. We got colors. Use them. There's our river. We're putting a rectangular field along this river. Now, ooh, that doesn't look so great, but we get the idea. Let us think about our dimensions. What do we have that's limiting us? We only have 600 meters of fencing. So that's a limiting thing. But otherwise, we got nothing else to kind of go off of. So at some point, we just got to start calling something x. The length of the fence along these two sides, that's going to be x. Well, let's think about the domain then, since that's our first problem. If we only have 600 meters, technically, I mean, I guess you could put fences right up next to each other. What's our domain? Between 0 and 300. You hope that it's at least like an inch long and maybe 299.9 foot, or meter, excuse me. I guess we're talking about meters, so I should be talking about centimeters. Just a ridiculously thin fence in field somewhere. But one side can't be more than 300, because if it was, then we wouldn't be able to create a rectangle. If these are both 300, that'd be all 600 meters of your fencing. So we have to talk about how do we label this other side. We don't know what it is, and it doesn't have to be the same length as the x's. So you have to think, we could call it y, but how would we then solve for it? We don't have many things going on. All we have is that there's 600 meters of fencing. So we're not going to call this length y, even though it is unknown. We're going to write it in terms of x. So here's what I want you to think about. We have 3 sections of fence. This is going to take x meters. This is going to take x meters. So I kind of just unfolded it. And we only have a total of 600 meters. So what could we call this inside part, this length right here that I'm trying to give a label to? Well, if the whole thing is 600 and we're taking away, or we're using, 2x worth of fencing, that would leave 600 minus 2x meters of fence left over. When we add up these 3 things, we get 600. So that's actually what we're going to label this as. 600 minus 2x. Now, you might see this all coming together. What is the maximum area? How do we find the area of this field? Length times width, x times 600 minus 2x. And there we have it. We have stumbled upon our quadratic model. The section we are in, we're looking for quadratics. So to maximize the area, let's distribute that x. I'm going to actually flip the terms around just for the fun of it. How do we find the maximum for something quadratic? I want you to think about this graph right here. Where is its maximum? The vertex. We're going to use this to find the vertex, which we talked about last week, or you watched me do last week. Opposite of b over 2a. Negative 600 over what? Negative 4 equals 150. So it looks like our x value is 150. What is our area at 150? Plugging in 150 into this, I'm going to save you the calculation. I'm going to do it myself. Or I guess I should say I already did it. 45,000. We get that from plugging x back into our function a. So what's the max area? It's 45,000 square meters. And what are our dimensions for that max area? It is 150 meters by, let's plug in 150 here. 2 times 150 is 300. 6 minus 3 is 300 meters. So we're going to do 2 more. We're creating functions that we are going to maximize or minimize using quadratics, because we know where a max or min has to happen, the vertex. So I'll be right back with our next problem. Again, magic. Next word problem. The price of an item is modeled by P of x equals negative 1/3 x plus 100, where x is the quantity sold. Recall that revenue is the price times the quantity sold. That's how much money you're taking in, different than profit. We're answering three things. What price is the revenue maximized? How many units are sold at that price? And then find the maximum revenue. So we're going to do the same type of thing. We're trying to maximize something. And right now we're thinking about if we know a parabola, we know where the maximum is. It's at the vertex. So if we can come up with a quadratic model, we can find the maximum by locating the vertex. And the vertex is going to give us a handful of these answers. So let's talk about our revenue function, price times quantity. What's the price? The price is P of X. What's the quantity sold? That's X. So I'm going to replace P of X with its expression, with its equation or whatever. R of X equals negative 1/3 X plus 100 times X. And if you notice, when we distribute our X, our revenue function is a quadratic. So if we want to maximize the revenue, which is a quadratic, we need to find the vertex. So again, similar process. We're going to do the opposite of b over 2a, which in this case happens to be, opposite of b is negative 100 over 2a, negative 2/3. Remember, dividing by a fraction, multiply by its reciprocal. Hopefully you can do this in your head. Negative 100 times negative 3/2 equals 150. There we go. Sorry about that. Our revenue is maximized when, so we solved for X. X is the quantity sold. So we maximize the revenue when 150 units are sold. How do we find the max revenue? Well, we need the price first. No, we don't. We just need the units. I'm sorry. For the revenue, we just plug it in. So the max revenue, sorry about that, is just when we sell 150 units, which I'm going to tell you, $7,500. And finally, when it asks for the price, so that was the second question. I answered the third before the second. How many units are sold at that price? No, I'm doing this backwards, aren't I? I found the second question. That's the answer to number 2. That's the answer to number 3. How do we get 1? Well, when 150 units are sold to find the price, we plug it in to the price function. 1/3, negative 1/3 of 150, which is negative 50 plus 100 equals $50. There is our price for when the revenue is maximized. We got one question to go. I'm going to pause and write it down, and then we'll come back to that. Our last question. A farmer, maybe it's the same farmer, wants to build a rectangular triple corral. This guy loves rectangles with 800 feet of fencing. Maybe it's not the same farmer. We did the first one in meters. What are the dimensions of the corral? What is the maximum area enclosed? In calculus, when you learn about derivatives, finding maxes and mins will be a little bit faster of a process. But for right now, the only thing we know how to maximize, or find the maximum of, kind of off the top of our heads, is a parabola. So we got to find a quadratic equation to model the area of our triple corral. It is a rectangle. Again, we got to call something x. So I'm going to call this one x, which means all 4 of these have the same length. Let's figure out what we would call the other 2 parts. So remember, we have 800 total feet of fencing, but we're using 4x's worth. And then with whatever's left off of this, it has to extend across the top and bottom. So what do we have to do? We have to divide that by 2. So what are we going to label across the top and the bottom, if you'd like? 400 minus 2x. So that is how we can represent one side in terms of x. Thinking about our total, what we've already used, and how many other places we have to use it in. So total minus all those 4 x's cut in half because you have to use half down there and half up there. With those labels, this might be the time where you pause the video and you run through the problem yourself, see if you got it. I'm going to walk through it, so if you don't pause, you're just listening to me, but I would recommend trying it yourself. How do we find the area of this rectangle? X times 400 minus 2x. Distributing that, 400x minus 2x squared. And again, for the last time today, to find the max, we need to know where the vertex is. So we're going to do opposite of b over 2a, which is negative 400 over 2 times negative 2 is negative 4, is 100. So it looks like we have one length right here. This length right here is 100. How far would it be across the bottom? Well, 400 minus 2 times 100. Well, that would be 200. So what are our dimensions? 100 by 200 feet. And then what is the maximum area? I mean, you could just see what the dimensions are and multiply them, or you can plug in 100 into your function, which gives you the same thing, 100 times 200, which is 20,000 square feet. Okay, on Friday, we're going to be doing some practice. We're going to start with a class kick and try that out, and then we'll move on to the homework. You'll be working together again, just like kind of last time, and yeah. Hopefully this went well. You can pause, you can go back, you can rewatch things. One of these days I'm going to have to pay someone with Adobe After Effects to create a graphic to introduce myself, because seeing me pop up on screen saying hello is going to get annoying. I'll see you in a couple days, or maybe you're watching this an hour before class. Kudos to you. Well, I'll see you later. Have a good one. Yay, Precalculus.